Last time we wrote the Hamiltonian for a hydrogen-like atom, and the expression that we wrote down is this one here, with the expression for the potential energy written in here. And let me say something more about the potential energy, because in general, the expression for the potential energy is usually written like this. So it's minus the charge of the first particle that I'm going to call Q1 here, Q2, which is the charge of the second particle, and then we have here we have R, but we also have a constant here, which is 4 pi epsilon 0. This constant here also appears in the Coulomb law, usually, right? And in Gaussian units, epsilon 0 is chosen such that it is equal to 1 over 4 pi. So the units are chosen such that this constant is equal to 1 over 4 pi, so that this term here will be equal to 1. So here we are implicitly using Gaussian units. So it is nothing major, but I just wanted to point that out. What we want to do now is we want to write down the Schrödinger equation. Okay, we want to write down the Schrödinger equation and try to solve it. Okay, but in the solution, what we want to find, actually, it is not really the wave function itself. Of course, it can be derived, but what we really want to find is the spectrum of the energy. So our main target here, our main objective is the spectrum of the energy. And in order to do that, we need to start from the Schrödinger equation, which is I h bar d psi over dt equal to Hamiltonian acting on psi. And we will start the derivation by using the method of separation of variables. Separation of variables, where we have to assume that the function psi, which depends on the position x, in this case it is the position of the electron, t, and this is equal to some function psi 0. I will denote it by psi 0, which depends only on the position x, and we have to multiply this by a function f of t, which depends only on time. So this is how we want to separate variables. Okay, and we still have to do several steps in order to derive the spectrum of the energy, and we will see it. So it will be non-trivial to do the derivation, but I will do it step by step, so that you can follow quite easily what I'm doing. Okay, so the spectrum of the energy, it is something that it is not very straightforward. It was not straightforward in the early beginnings of the 1900s. Okay, because it was found after some experiments that the energy levels of the electron could be discrete, but according to classical mechanics, that was kind of strange, kind of weird. Plus, the electron moving in a circular orbit was something strange. I mean, that was the idea at the time, that the electron should move on in a circular orbit or something like that, in a closed orbit around the nucleus, and in doing so, it should emit electromagnetic waves because it is accelerating, right? And this emission of electromagnetic waves would lead to a decrease in the energy of the electron. And therefore, the electron, after some time, would have had to collapse into the nucleus. But that did not happen, would not happen. Some people also calculated the time that it would take for the electron to collapse uh, into the nucleus. And amazingly, some scientists found that this calculation led to a very, very small number. So it would mean that if the theory of classical physics applied to atomic particles as well, it would simply mean that no atom would exist, because the electron would collapse into the nucleus, and it would be unstable, incredibly unstable. So this is very important to understand that quantum mechanics led to an incredible explanation for that phenomenon. And at first, some other people tried to describe the behavior of the electron in a hydrogen atom, for example. And yes, they managed to derive some ideas to, let's say, to write down some some equations, but from empirical facts. And there was no theory. The theory that helped understand the behavior of these particles and of these atoms was quantum mechanics. And this is where we had to start from. So we have to start from the most important equation in quantum mechanics here, which is the Schrödinger equation. And from here, we have to, to derive everything else. So this is what we have to do. This is the starting point. It is just, it has to be the starting point. So that's why we have to start from the Schrödinger equation. Okay? And we have to substitute this expression into the Schrödinger equation. And I will start doing the derivation in the next video.